8.3 vector, parametric, and symmetric equations of a line in R cubed. Okay, so this time we're talking about R cubed, not R squared. Everything that we're going to do is going to look very familiar. It's just going to be extended by one coordinate. So instead of xy, we're going to deal with xyz. So in R cubed, which is like 3D, if vector r naught equals x naught, y naught, z naught, it is determined by a point on the line. And direction vector m is now going to be ABC. So one extension onto that. Okay? So now our vector equations are going to be the same, except for our r naught is going to be x, y, and z, and our direction vector m is going to be a, b, and c. So it's going to look very, very similar. It's just going to be extended by that z component. Okay? And r naught is a vector from the origin to the point on the line. And vector m, the direction vector, has components a, b, and c. Okay, likewise, the parametric equations, instead of just having x and y, we now have to break down that vector equation into x, y, and z. So we have the point x, y, z, and then we have a, b, c, which is the direction vector. Okay, and the parameter is still an element of the real number system. Now, symmetric equations, this is a little bit different. So symmetric equations of a line in R cubed, what we're basically doing right here is we're going to take the parametric equations and we're going to isolate for t. And we're essentially going to have t equals t equals t. Okay, we're going to have some expression of t equals some expression of t for like the y's equals some expression of t for the z's. And we're going to get deeper into that in just 1 second, okay? So note that all three of these equations depend on the other ones. Okay, so by knowing one of these equations, you'll be able to know all of them. The vector, the parametric, and the symmetric. Example 1. A line passes through the points A and B. Calculate possible direction vectors for this line. Okay, so we know that direction vector AB is going to be the B minus A. So -3 minus -1, comma, 3 minus 3, comma, -4 minus 5. Okay, so -3 plus 1, I get -2, 0, -9. There is a possible direction vector for the line that passes through AB. So this question asks us to calculate possible direction vectors, okay, with an S. So this is going to be vector AB. So now vector BA is going to be the exact same thing, but we would have subtracted -1 minus -3. So essentially what happens is we're going to take vector AB and multiply it by -1. And again, it's going to be an equivalent vector. So I get 209. Okay, we could also have like 2 of BA, and we can multiply this one by 2. And I would get 4, 0, 18. And we can keep going, but there are 3 different possible direction vectors for this line. The only thing that's changed here is that instead of having x, y, in 2D, we have x, y, and z in 3D. Example 2 asks us to determine the vector and parametric equations of the line passing through P and Q. So first what we need is a direction vector. Okay, so let's find the direction vector PQ. So what we're going to do is we're going to do Q minus P. So -2 minus -2, comma, 4 minus 3, comma, -1 minus 5. Okay, and what do we get? 0, comma, 1, comma, -6. Okay, so all we need for a vector equation is we need a point. So let's just put point P, -2, 3, 5, -2, 3, 5. And it doesn't even matter which one we choose, P or Q. And then plus some parameter, and then our direction vector. That's done. Okay, so there's our vector equation. Now, parametric equations are going to be x equals y equals z equals. I never actually write them all the way across. I actually write them down. Negative 2, 3, 5. So negative 2, 3, 5. The first one's plus 0t, so we can just leave it. The second one's just plus t, plus 1t, and then minus 6t. Okay, there's our parametric equations. That's done. Example 3. Show that the following are vector equations for the same line. Okay, so we have L1 and L2. In order to be the same line, what we want to do is we want to check the direction vectors. Okay, so let's check direction vector D1 and direction vector D2, and we want to ensure that they are some multiple of one another. So when I look at these, I know that negative 1 times 2 equals negative 2. 2 times 2 equals 4, and 5 times 2 equals 10. So therefore, I can say direction vector 1 equals 1/2 of direction vector 2. Okay, or we can write it D2 equals double D1. Right? Either way, we know that these lines are at least parallel. Now what we want to do is we want to prove that they are coincident. And that just means that they're exactly the same lines. They lie right on top of one another. So what we can do is we can take the point from the first line and we can sub it into the parametric equations of the second line, or vice versa. Okay, because both of these points should satisfy both equations if they're the same line. So if we had x equals 4 minus 2m, what we're going to do is sub in that negative 1, 4 minus 2m, bring that over, negative 1 minus 4, and then divide out that negative 2. I get 5 over 2 equals m. Okay, so if I were to sub in this negative 1 into the x parametric equation of L2, it's going to give me 5 over 2 for the parameter m. Now we're going to continue to go on. Let's sub in 0 for the next one. So 0 equals, and now we're going to take the y, the parametric equation for the y in L2. Negative 10 plus 4m. Negative 10 plus 4m. Okay? Bring over that negative 10, we get 10 over 4 equals m, which is 5 over 2. So far it's looking good. Okay? So we get the same parameter for negative 1 and 0. Now, let's test the 4. And I'm just going to squeeze this in here. 4 equals, so for the z components, we get negative 21 plus 10m. Okay, so let's bring that negative 21 over. We're going to get 4 plus 21 divided by 10 equals m. So I get 25 divided by 10 equals m. Let's reduce that, divide both by 5. I get 5 over 2. So therefore, equals m. Therefore, because I can get the same parameter with all three, and the direction vectors are multiples of one another, these are actually the same line. Okay, this question is very similar, but what we're going to do this time is show that these are vector equations for different lines. Okay, so first let's actually test the direction vector. So I get negative 1, 1, and 2, and I get 1/2, negative 1/2, negative 1. Okay, so negative 1 divided by negative 2 gives us a half. 1 divided by negative 2 gives us a half. 2 divided by negative 2 gives us 1. So actually D1 is a multiple of D2. D1 equals, let's go, negative 1/2 of D1 equals D2. or d1 equals negative 2 of d2. So what we want to do now is we want to test if, I'm going to test if this point lies on our first line. The reason why I'm going to do that is because then our parametric equations are not going to have fractions in them. Okay, so our parametric equations for L3, we can list them first if you want, if that makes you more comfortable. 161, and I write them down. Negative t plus 2t. Now let's test if negative 3, 10, and 12 have the same parameter. Okay, so let's sub in negative 3 and isolate for t. Negative 3 minus 1 divided by negative 1. I get t equals, that's negative 4, so positive 4. Okay, now let's sub in, draw this line, sub in the y. So I get 10 equals 1 plus 2t. Okay, isolate 10 minus 1 over 2 equals t. I get 9 over 2. We can actually stop there. Since we would have to sub in a different parameter, oh, I put t. I'm so silly. This parameter is actually L. So these should have been L's. I'll do it in a green. These should have all just been L's simply. No big deal, but the form's off. Okay, it doesn't change the answer, but the form's off. Okay, so we would have to sub in different numbers for the parameter L in order to get the point negative 3, 10, and 12. Therefore, negative 3, 10, 12 does not lie on this line, so these are indeed different lines. Okay, so just a little bit of an investigation about the symmetric equation of a line. So symmetric equations of a line are derived from using the parametric equations, which we have actually right here. And basically what we're doing is we're isolating for the parameter. In this case, we're isolating for t. So if we brought over that x naught, so x minus x naught, and then we divided out that a, that would be our expression for t, for the parametric equation for x. Okay, likewise, we bring over this y naught, we get y minus y naught over b, and this for z we get, I'm just going to put it down here because I don't want to squish it in, z minus z naught over c. So there are three parametric equations, or sorry, there's our three equations when we isolated for t. Okay, and just note that the denominator cannot equal 0. So A, B, or C cannot equal 0 in symmetric equations. Okay, so because we know T equals T, obviously, we know that x minus x naught over A is going to equal y minus y naught over B, and that's going to equal z minus z naught over C. And that's how we get our symmetric equations. So example 4, write the symmetric equations of a line passing through the points A and B. So what we need first is we need to, we can write it in the vector equation first. So let's write negative 1, 5, 7 plus some parameter, but then we need a direction vector. So let's say, just on the side of the paper, AB, direction vector AB. Negative 3 minus negative 1, comma, negative 4 minus 5, negative 4 minus, and I'll just continue here, 5, comma, 8 minus 7, 8 minus 7. Okay, so our direction vector is going to be 4, comma, negative 1, comma, 1. 4, negative 1, 1. So if we put these into parametric equations, and this is lots and lots of practice, negative 1, 5, and 7, 4, negative 1, 1, plus 4t minus t plus t. All we have to do from here is rearrange. So I get x, and I'm just going to bring this over, plus 1 divided by 4. equals y minus 5 divided by negative 1 equals z minus 7 divided by 1, or you can just leave it. And these are your symmetric equations for the line that passes through AB. Exactly the same question, write the symmetric equations for the line that passes through P and Q. Okay? This time I'm going to start with the direction vector PQ. Okay? 4 minus negative 2, comma 3 minus 3, comma negative 5 minus 1. Okay, so I get 6, 0, negative 6. This is our direction vector. So we can go ahead and write a point and then plus some parameter t, 6, 0, negative 6. And what I forgot to do on the last one is put t as an element of R. Okay, from here, make your parametric equations. So we can put x equals, y equals, and z equals. And we put negative 2, 3, 1 down, and then plus 6t. The second one's not going to have any t's. You can put plus 0t if you need to see that, but I'm not going to do it. And then the last one's minus 6t. So if we were to rearrange these to isolate for t, so we bring over the negative 2, and we get x plus 2 over 6 equals, okay, I'm going to skip the y equals 3 for 1 second, and I'm going to bring over this positive 1, so we get z minus 1 over negative 6, okay, and then I'm actually going to put comma y equals 3. Okay, so if we're ever in the situation where we have 0 in front of the t, we can't divide by 0, right? Because that number would go down here. So we just write y equals 3. Okay, in part C, write the symmetric equations of the line passing through the points x and y. Okay, so again, let's find our direction vector. So let's go y minus x. So we get negative 1 minus negative 1, comma, 3 minus 2, comma, 9 minus 5. Okay, so our direction vector is 0, comma 1, comma 4. Okay, so let's just take any point. Okay, let's take negative 1, 2, 5. So negative 1, 2, 5. And if you notice this time, I actually skipped a step where I write the vector equation. Okay, and then our parameter is going to be plus 0t, so we don't have to put anything for x, plus 1t, plus 4t. Okay, so the y and the z are just like normal. Y minus 2 over 1, and that equals z minus 5 over 4. And then what we're going to do is we're going to put a comma, x equals negative 1.